Oh, another black screen Commodore 64. I wonder what's the problem with this one. Oh, what? Okay, yeah. Just as I thought. The PLA from this board is bad. Another dead PLA on a Commodore 64. Okay, well, it's not a problem. I'm just gonna make a replacement PLA. Alright, so that was a little bit of a dramatization. I didn't actually have a PLA problem. Well, at least not with this machine right at this moment. But if you watch any of my repair videos in the past, you know that I've had PLA problems a whole bunch of times. It's a very common failure on the Commodore 64, and it results in nothing else but a black screen. Well, almost always. Now, even though that was a dramatization, I wasn't kidding about making a new PLA. But before we get to that, let's talk about what the PLA actually is. The motherboard you see here is what's called a long board, and it's the most common thing you'll find in any bread bin Commodore 64. The PLA chip is this chip right here. The position of the chip can change depending on which motherboard revision you're using, but the marking on the board says U17 next to the socket, and that doesn't change, although I think on the SX64 it might have a different designation. But on the long boards, it's always going to say U17. Now the PLA, which stands for Programmable Logic Array, always has the marking 906114-01. There are a couple other markings you actually might see, like 82S100, and I think there's one other one that's possible. But generally, you'll see the 906114-01. Now the aforementioned 82S100 was actually a programmable chip, which is where Programmable Logic Array comes from. But these 906114-01 chips are not programmable. They are actually manufactured already with the programming contained inside of them. But the name PLA or Programmable Logic Array has just stuck, going back to those earlier chips that were actually programmable. Now, what does the PLA do, you might ask? I mean, you know that when they go bad, it results in a black screen. But why is that exactly? Well, on an 8-bit computer like the Commodore 64, the CPU has 8 data bit lines which make up the data bus. And those data bus lines are shared amongst all the peripherals on the computer, like the cartridge slot, the graphics chip, the ROM chips here, the interface chips, and even the RAM. All of that sits on that same bus. But only one of those things at a time can be electrically connected to the bus and driving it. If two things at the same time try to communicate over the bus, like say one of these ROM chips and the VIC graphics chip, what happens is you have a bus conflict, and the computer behaves erratically or doesn't work at all. And that's where the PLA comes in. It acts like a gatekeeper and regulates which of these peripherals is able to communicate on the bus. Now, there's nothing super special about the PLA, but at the time when this computer came out, it was pretty cool that Commodore used it, because what they did is they removed a whole lot of discrete logic chips like that you might find on a Commodore PET that did the same function as the PLA, basically controlled what could talk when, and they reduced it down to just this single chip. It's one of the reasons why the Commodore 64 is so powerful and yet has so few chips, because essentially you have primary function chips, CPU, ROMs, SID, graphics chip, I/O chips, cartridge, but there really aren't a lot of other support logic chips. If you subtract the 8 RAM chips that make up the 64K and the SRAM chip that's used for color RAM, you're only left with just a few actual support logic chips on the entire computer. So we know the PLA is an essential chip, and this here is a selection of bad PLA chips that I had in my bad parts bin. Without this chip, you're not doing anything on a Commodore 64. It's absolutely essential. Now, I'll put a link in the description to a good video talking about the PLA and why these fail so much, but I'll boil it down to something simple, that MOS, when they were making these chips, used a process that is very prone to decay and failure. So over time, these chips simply go bad. Now you might be asking, if the original 64s had that 82S100 programmable chip, which gave the PLA its name, why can't we just get those chips, program them, and stick them in the board? Well, unfortunately, there's two reasons. One reason is it's pretty much impossible to find those chips anymore. They were really a technology of the late 70s, and by the time the Commodore 64 used it, it was late in the life cycle of that chip, which is why Commodore switched to making their own PLA. But there's actually another reason. Even if you could find one of those blank chips, the hardware required to program them is next to impossible to find. You need very specialized older equipment to program them. And the Common Mini Pro, which I've showed many times on my channel, is just not capable of programming those 82S100 chips. Now, the fact that PLAs fail isn't new, and people have been trying to make replacements for a long time. And there are all sorts of different attempts that have come and gone over the years, and some have been much better than others. I'm holding in my hand one of the more recent solutions to the PLA problem, and it's called the Platinum. This uses a CPLD to replicate the PLA. It comes with this nice document that actually talks about what the PLA does and some of the problems with replacing the PLA with more modern things like the CPLD. Some of the specific issues with the different revisions of motherboards are timing problems, and this especially is important because of different electrical characteristics of the components used on the different motherboards. Those slight differences in the motherboards actually has the side effect of making this not work universally in all of the motherboards. The kit came with this small capacitor and instructions on the back of the sheet on how to modify your motherboard and correct those slight variances to allow this to work more universally. Okay, let's try out the Platinum in this Commodore 64. This is a 250-426 motherboard, one of the later revisions that has the 8701 timing chip. As you can see, this computer is working. I have an actual MOS PLA in here, and I haven't done any modifications to this board whatsoever. We'll turn this on. Has a little blue LED on it. And sure enough, there we go. We have a working computer. Excellent. Okay, what you see here is what's called a Rev A motherboard. It's one of the earliest Commodore 64 motherboards, came out in 1982, has these gold RAM chips, and the one differentiator is the video port only has 5 pins, so it's lacking that Luma, Chroma, or S-Video type output. We can see that this thing is working fine with this PLA in here. I'll remove that PLA, turn it on. Well, and check it out, we have a black screen. The blue LED is running, but the machine is not working. According to the paper here, it says the Model A motherboard has some timing specific components and requires installation of an 82 ohm cast RAM resistor and a timing capacitor at C204. And finally, we have my ZIF 64, which is revision 25407. I'd say this is the most common. I have a lot of these motherboards. I find these a lot. The PLA chip is up here on this one. So remember on that first board, it was down there. So they've switched the position, but it's still marked with U17. Let's turn this on. So you see this is working fine with this original MOS PLA in here. We'll take that out. There we go. Turn this on, blue light. And we have a black screen again. Let's go back to the paper. 25407. This board has a cast RAM resistor, but usually requires installation of a timing capacitor at C204. So there we go. So far, 2 revisions out of the 3 that we've tried haven't worked. All right, so what would you think if I told you you can make your own PLA and you can do it for about $2.60 US, and it has really, really wide compatibility, doesn't require any modifications to any of the Commodore 64 so far that I've tried, and it's all made with very easily obtainable parts, and you can solder it yourself at home without any special skills. It almost sounds too good to be true, right? Well, let me introduce you to the GAL PLA. The GAL PLA project was conceived and designed by Daniel Mantian, and I'm probably butchering your name, Daniel, I apologize. He's out of the Netherlands, and he decided to come up with a way to replace the Commodore 64 PLA with very easily obtainable products or chips with a design that was freely available to download that anyone could make. And on today's video, I'm going to build one up from scratch and show you which parts you need to order to do it yourself and show you exactly how much it all costs. Daniel has a great website online now, which I'll link to in the description below, about how to build one of these yourself and a lot of other background information on the PLA. His project is based upon original reverse engineering done by Jens Schoenfeld. Sorry, Jens, I'm probably screwing up your name. Daniel's idea was to make a PLA that was so easy to make, it had to be made with components that were also easy to obtain. So he ended up picking the Lattice Gal 20 V8 as the chips to use on his project. These are very easily obtainable from China right now for just a few dollars for a package of 10. He does mention that the Gal 20 V8 is no longer in production, but it was so ubiquitous and used in so many places, it's readily available from China right now. I even looked through some of my spare parts bin and found some Gal 20 V8s on some old video cards. They're seemingly everywhere, especially in equipment from the 90s. Now, Daniel goes on to talk about how good this PLA replacement is. Now, this is where I came in. I actually helped him with testing of various things on this project. One of those things was Super Zaxxon, a rare cartridge that's kind of a bellwether test as to whether a PLA replacement's going to work. Let's check out some footage of me testing his project with a Super Zaxxon cartridge. First up, we're going to test the original Commodore MOS PLA chip, just as a control to make sure that Super Zaxxon is working. So Super Zaxxon into the machine. So when we turn this on, joystick or keyboard, we'll do joystick, and we'll do one player. And apparently, right away, the issue manifests itself with graphical corruption. So stock PLA, everything seems to be working without any issue. All right, let's pop out the original Commodore PLA. Drop that in. All right, moment of truth. Joystick, one player. Whoops. Well, that's looking good now. I don't see any glitches. Right, so awesome. So the 25 nanosecond chips in here, working great. No graphical corruption whatsoever with Super Zaxxon. As you just saw, the Gal PLA works perfectly with Super Zaxxon, and I tried it on a couple different machines, and it all worked on all of them. Another good test is whether you can use a replacement kernel with the EasyFlash 3 cartridge, and the answer to that is yes. Apparently the EasyFlash 3 does all sorts of trickery to get a kernel loaded from the cartridge slot without any additional wiring, which is normally what's needed to change a kernel, and it works perfectly with this project. One thing that Daniel and I have not been able to test yet is the Epyx FastLoad cartridge. I don't have an authentic one of these to test with, and nor does he. So hopefully someone can test this out and get back to us. I used my logic analyzer to test the CAS to CAS-RAM delays and also the game to ROM-H delay times, and everything seemed to be in spec for what you'd expect from a PLA, which is likely one of the reasons for the high compatibility. I also measured the rise and fall time with my oscilloscope, and while it's not a perfect match for the original PLA, it seems to be close enough to not cause any problems whatsoever. On his webpage, he has a link to PCBWay, so you can have your own boards made, or you can get the Gerber files to make them at your own producer, or you can contact Daniel directly if you want to just get a PCB from him. And at the bottom of the webpage, he has the source code so you can check it out yourself. And he also has the JED files for programming the Gal chips, which we'll do right now. All right, so what will you need to build one of these for yourself? First, you'll need some PCBs. These were made at PCBWay, but it's a tiny little board, so it's inexpensive. It's always going to be the minimum price, and you can get them made at any of the Chinese manufacturer or Osh Park if you so desire. Next, you'll need some Gal chips. These are the Gal 20 V8s from AliExpress. They are 25 nanosecond variant, and they cost $4.17 for quantity 10. Then, optionally, if you want, you need a couple sockets to install onto the PCB, although you could just solder these directly onto there. I don't recommend it. I recommend you just buy some inexpensive sockets. I got 20 sockets from AliExpress for $1.61 shipped. And then you need some pin headers. These will solder into the PCBs and allow you to connect into the motherboard socket for the PLA. And then the very last thing you're going to need is something like this. This is a TL866 Mini Pro EEPROM programmer. This is what is used to program the Gal chips. There are all sorts of other alternatives for programming them, so you don't need to use one of these, but I've used this on my channel quite a bit and I highly recommend it. This is one of the older versions. You can't get these anymore. The newer one looks exactly the same and will work for programming these gal chips. And that's what you're going to find. I'll have a link in the description. Right now, the TL866 programmer costs about $38 shipped from AliExpress. Of course, it goes without saying you're going to need a soldering iron to assemble this, but it's all through-hole parts, so it's very easy, and you can use any soldering iron, even one of those cheap $3 ones from China, if you so desire. All right, enough talking. Let's put this thing together. First off, let's just check out the one that I've already built. So the PCB has 2 sockets, and there's the 2 gal chips in there, and on the bottom, you'll see the pin headers, which are these things, and this is what plugs into the motherboard. When you look at the PCB, you can see the outline for the 2 sockets. They go right here and another one right there. And you see the outline of the original socket with the notch on the top that is for the PLA socket on the motherboard. So first off, we need to cut these strips down to length. So it goes in the longer set of holes, so you just stick it in there and use something to break that off like that. And we do it twice. Make sure you don't miss a pin or you're going to need another set strip of those. Whoops, that one just went flying. So there we go, those are cut down. So when we look at these headers, they have a longer part and a shorter part. The longer part is what goes into the motherboard socket, and the shorter part is what we're going to solder onto the PCB. Now what I recommend doing to keep these straight is put them into the PCB like that and like that. And you see how these are all wobbly right now? We can't just solder those on, or we're going to end up having a hard time sticking it into the socket. So I recommend taking something like a 64 or just a bare socket, and you stick the pins into the socket like so, and then we'll put the PCB on top of those pins, and you might have to kind of bend it around to get it to go in, but there it is. It is now on those pins perfectly. And then what I'm going to do is I'm going to solder a couple of the pins onto the PCB. Not going to do all of them because I don't want to transfer all that heat into the motherboard, but let's just do a couple of them. Just like this. One there. One there. So that's enough to keep those pins nice and steady, and we can gently pull this out. And you see now this is on there, nice and straight, and I can go ahead and I can solder on the rest of these pins now. All right, so everything is soldered on there and looking good. Pins are straight. So now it's time that we're going to install these sockets. Now you have to install the pin header first. You got to do the socket second, otherwise it's impossible to put this thing together. And then you carefully flip it over, do the rest of this soldering. And just like that, we're done with the soldering. And this is all the work there is to do when it comes to assembly. All we need to do now is program those chips and get them onto a Commodore 64. All right, so programming the gal chips, we're going to need these JED files to do the programming. And remember, there are 2 gal chips. There's a left and a right. So he has them marked L and R. Now, the R file says it works with both 25 nanosecond and 15 nanosecond gals. You'll find that when you buy them, both are available. I recommend you get the 25 nanoseconds if you can. But if you can't, you get 15, they can still work. For the left chip, I recommend you use this top one if you're using 25 nanosecond gals. For the 15 nanosecond, there may be some timing problems, which I did experience in my testing of Super Zaxxon. But these other alternative files, specifically the L-Alt2, is designed with extra delay in mind. And he says you can program this if you're using a 15 nanosecond gal, and it will work, and it works perfectly with Super Zaxxon. He does say it will work on a 25 nanosecond as well, but I haven't tested that. But I recommend you use this first file if you're using 25 nanoseconds. Now we have the JED files. Programming these gals is ridiculously easy. We're going to stick it into the programmer and close the little lever. In the software, we're going to go and change the configuration type to all, and we're going to type in GAL20, change it to lattice, and we're looking for the GAL20 V8B, like that one right there. We're going to hit select, open the file. We're going to program the L file first. So you see all these zeros and ones that are loaded in the software. Now we're going to say program, and I'm going to turn off the lock bit. What the lock bit is, it just prevents you from reading the gal in later and verifying it. So just leave that off. I mean, we're not trying to protect this software that's on here. So we're going to hit program. This just takes a moment. It will erase it again, program it, and it does a quick verify, and we're good. What I like to do is just take a marker and I program the L chip first. I'll just draw an L on there. And we'll take this out and we'll pop in the other chip. And this one is going to be the right chip, so we'll write R. Back in the software, we're going to open up the R file. And we're going to hit device program. Same thing, we're going to leave the lock bit off. Hit program. Programming stopped. Overcurrent protection. Short or IC damaged. And we'll just check the chip. It's definitely in there correctly. The dot is up at the top. None of the pins are bent or damaged. Maybe I had this. No, it was in there correctly. Let's just try one more time. Program. No, that's bad. So I guess that's the pitfall of getting stuff from China. Might get a bad chip. So I marked that with an X. Luckily, I have some more chips that I got from China. I forgot to mention, you can tell if they're 25 nanosecond because it says GAL20 VAB 25 there. If it says 15, then it's the 15 nanosecond version. So I'll just take another one of these off here. This is another 25 nanosecond lattice chip. I'll pop that in there. And now we'll try programming again. There we go. This one's working. So that chip definitely damaged or bad. How annoying. All right, programming successful. So I got to draw the R on this chip again, just so we don't mix them up. All right, now we just need to install these into this adapter. Now this one appears to have a bunch of bent pins. These chips definitely look like they were pulled out of pre-existing equipment. Like, I don't think these are fakes because they're sort of scratched up and they probably just are on some old e-wasted gear that got sent into China for reuse. But that's good for us because it means that we're probably getting genuine chips. So there we go. First one is in. That's the L chip. And the next one is the R chip, which also has a couple bent pins. And there we go. Both chips are in. Just do a quick check to make sure you didn't bend any pins. Everything looks good, and all the pins on the bottom, they look okay as well. So there we have it. One completed PLA chip. Now it's time to test this thing out. Okay, let's start back with this original machine. This is the later version with the 8701. We'll pop this in. There it is. And let's turn it on. Is it going to work? There we go. Look at that. It's working. We'll do a little bit more testing in a second, but let's just quickly test those two other C64 board revisions. Next up is the ZIF64. Let's try Daniel's PLA. There we go. Power it on. Boom, blue screen, looking good. And finally, we have this Rev A board, which are very problematic. It required two separate mods to allow it to work. I'm checking to see which of these is which. So the socket on the right is U18, that's the SID, but U17 is the PLA. And Daniel nicely wrote C64 U17 right on the PCB. So in case you forget, it's right there. There we go, goes right in very easily. And moment of truth, here we go. Look at that, it works. It's so functional, this chip. It works in everything perfectly. Now really quick, let's move this Rev A board back to the original PLA. So this was the PLA here that I got in it. This is one of the MOS chips. Definitely not the original chip. I guess what happened is at some point, probably the original PLA failed in this, got replaced with this one, or I don't know. By the time I got this, it was different. Okay, so that's the MOS PLA. Let's try the Easy Flash 3 cartridge in this machine. Because from my own testing, while you get the startup screen, if I try to load anything at all, you get this, garbage and corruption. This does not work. There is a mod you can do on this motherboard to allow the Easy Flash 3 to work, but it does require soldering some stuff on here. But what I'm curious about, and this is totally untested, is what if I take Daniel's GAL PLA, put it in, will it then work without modifying the board at all? All right, let's just make sure the machine is working. There we go, blue screen. Pop in the Easy Flash 3 cartridge. And there we go. And now if I try to load something, no, same fault. Okay, so it doesn't cure that particular issue, but I know the mod to fix this board is not hard to get this cartridge to work. Well, switching back to the 250-425 board, the later version, There is no problem with Easy Flash 3 working on this board, even with Daniel's thing. So we can, this keyboard does not work properly. There we go. And we can load DK Arcade. And there is actually a SID chip in here. Let's plug this in to audio for a little arcade, a little 8-bit. Oh, yeah, we know what this is. It's time for an 8-bit dance party. Okay, I'll spare you the dance party, but I would do it because it's pretty cool that everything works perfectly here. Now I can load alternative kernels. Like here is Jaffe DOS working perfectly. I wanted to also show the GAL PLA installed in an SX64. My friend Brian was able to build one up, and here it is installed in his SX64. It not only fits perfectly, but it works perfectly. All right, let's talk about pricing and what this would actually cost to make one of these boards. So you can get it down to $2.65, but that is the caveat that you're making 10 of them and that you already have a way to program the GAL chips. So to go through all these items, it costs $13.23, including shipping, from PCBWay for 10 of them. Then to order 20 of the GAL chips costs a total of $8.34, including shipping from AliExpress, or at least it did at the time that I ordered these parts. The pin headers cost $3.28 for enough of them to make all 10 boards, and you need the 24-pin narrow sockets. You'll need a total of 20 of those for $1.62. That comes out to a total of $64.62, which is $6.46 each. But keep in mind, that is including the TL866 programmer. If you exclude that, you're spending a total of $26.46 or $2.65 each. Now, you could make 10 of these, keep a few for yourself, sell the rest to friends who need PLAs for their 64s, or just keep them for inevitably when other people's 64s will die and you're like, hey, I have an extra PLA chip I can give you. I mean, any way you look at this thing is just a great value. Well, there you have it. Daniel has created something that is absolutely amazing and a wonderful gift to the Commodore 64 community. As far as I can tell, this GAL PLA achieves 100% compatibility, at least with 25 nanosecond chips. I've tested these far and wide on as much hardware as I can get my hands on, and everything has worked flawlessly. The only tiny issue I ran into is using the 15 nanosecond GAL chips. Super Zaxxon did have some graphical corruption, but flashing that special JED file that Daniel did that adds extra delay to the lines fixed the problem in Super Zaxxon. Daniel's website, which I'll link to in the description below, has tons of information about all the timing and testing that we did. And if you build one of these up and offer some feedback, especially if you find incompatibilities, please let him know. You can reach out to him on that website, and he'll update it with additional information there. Well, if you like this video, I'd appreciate a thumbs up, but if you didn't, you know what to do. You can hit that thumbs down button. You can subscribe for more videos. There'll be lots more in the future, and I'd love to hear your comments and your suggestions, especially your comments about this, in the description below. And that's it. Thank you very much for watching. We'll see you next time. Goodbye.